maximum. As you move away, the field strength keeps on decreasing. It infinitely be 0. I think this data is very important for you. You get plenty of application problems with the ring. So what all we take the numericals now. So we must have an idea of how the field varies and where the field will be maximum. And if you look at the ring, if you see the ring, not coming. Oh. Take like this. So now the current I, let it flow here. What is the direction of this? The axis? It's not a rod, some axis. How the B bar will be in this direction. What about B bar on this side will also be in same direction, not opposite, not like similar to, not like electrostatics charged ring. The field on either side on the axis of the ring will be directed opposite. No, on either side of the ring, or when on the axis, the B bar will be in same direction. Now, similarly, if the B bar if this is the axis, no, if the current flows in this direction, B bar will be in this direction. Basically, how B bar due to a ring will be. Basically, how B bar due to a ring will be. So if I plot, even they may ask you a simplest question, which particular diagram represents B bar due to a current carrying ring? You will be in a big trouble. So better, I think, in most of the books it is given, go through once, because all those things cannot be derived mathematically. A student must have a prior idea. All those things cannot be derived. So how the B bar, I'll show the lines of force. So here it should be one vertical line. This is on the axis. Then everywhere you show that increasing radius. It's a rough diagram. Please do refer some books where they're given diagram here. You may get surprise questions like this. There's no other way. Even in advance, they may ask you. So a student must have a prior idea of all this. So it will be uniform or non-uniform. Will be definitely non-uniform. I'm just showing only two rings. At every point, you should show that. So direction of this will be like this. Okay, got it. No, so this is about the B bar due to ring. So on the axis, we are able to predict. About any other point, it will be non-uniform. They may just trouble you. The B bar on the axis, as we move away, keeps on decreases. What happens even here also at point P1, P2? What do you say about P2? B bar at P2 will be less than that of P1. They may trouble you with in exams questions of these kind of. So the lines of force only will tell you, as the spacing between the lines of force increases, then what does the field strength? Field strength should decrease. Like this, at every point, you should assume a rings of increasing radius. So it's very important one. So all these diagrams you are supposed to remember. Okay, this is about the B bar. So next we'll take the under condition. Let me take a current carrying strip. Now at point P, I want the magnetic field where this will be at a distance of D, and let current per unit width be lambda and the width of the sheet let it be L. What is this? Current carrying sheet. So what is lambda? Lambda is current per unit width. We have to calculate the field strength at point P. So find field strength at point P. So what is the method here now? So, and it's a long current carrying sheet. Look at the width is L. So what actually the meaning of that? How that's a long current carrying sheet will be. So you can assume it. This will be infinity here, whereas the current here will be total current, let it be I. You can assume, and the current will flow here, and this will be the sheet. Look at these ends will be infinity, but this is it's having a width. L you write it, or you'll get confused. B, let me take it. It's not like a large current carrying sheet, long current carrying sheet. The width is how much? B, that one. So what is lambda? How you define lambda? Here you can define as I by B, current per unit width. Okay, no. So as such, we don't have any formula, no. So therefore, but we know due to long wire. So what this sheet shall we assume? Made up of a shall I say some element? I'll take it. So here, let it be dx. Let it be at a distance x from the point P. Now, in a width of B, what happened? What is the in a width of B? Let there be a current I. In a width of dx, how much of current? Try to analyze here. There is the charge in electrostatics for the charge here. Now it's all about the current we are going to define. So how much of current here? Let it be di. That will be like a long wire, thin long wire. So what is how we can define di by dx is equal to lambda total current per length. So di is equal to di by dx. This should be equal to lambda. So di is equal to lambda dx. Now calculate the field at this point. So due to small element, dB is equal to how much? Mu naught di 2 pi x, because like a long wire, no? And what is that green color strip? You can choose it to be somewhere here like this. If you want to become good engineer, you draw diagram. You want to just become one IITN, one rank, you will not draw diagram, anything, and you'll get a rank. It makes a difference. I'm telling you, it really do makes a difference. We have in India, what happened? Every year, what happens? I think some 10,000 engineers are coming out. 10,000 IITians with good rank are coming out, not engineers. We should not blame that the system is a problem, because even the advanced also nowadays, they're not giving diagram question papers. Earlier there used to be diagram based questions. Now what happened, they also have come to the standard of mains. They're also asking everything without diagram. So engineer, what happened, will be there in the physical world, no, not in imaginary world. So he will deal with physical things. Okay, no, let's substitute mu naught lambda 2 pi dx x, that one. And let's slide up. So dB is equal to mu naught lambda. Now what should be the limit? What are the, where the current is distributed from x equal to d to x equal to d plus b? The limit will be x equal to d to d plus b. So this should be equal to b equal to mu naught lambda 2 pi log of 1 plus b by d. So like how we spent in electrostatics finding out the E bar due to different charges system. Similarly here, different types of current carrying structures, and if you know the magnetic field due to that, you'll be in better position. Means you can deal. No, nobody will ask you find B bar of different current carrying structures. So what are the types of numericals? A charge particle is projected nearby sheet at a height edge parallel to the sheet. If you know field due to sheet, you can work out, no? Otherwise gone. The application part. So directly what I'll describe motion of charge particle. All any other applications, I'll bring it here.